So in this lecture, I'm going to talk about three mean squares. So previously we saw a mean square error, and now we're going to add two more to that. So in regression, we're going to have these three mean squares to help us compare models to each other. You've already seen the mean square error. And you're going to notice that these three mean squares follow the pattern of the general linear model, except we're using slightly different words, and we'll go into detail about those. So before we looked at this data with 4 students and their quiz grades and how many hours they spent watching TV, and we got a mean square error of 18.75. Okay, so what? Is that a good number? Is that a bad number? Well, we don't have anything to compare it to, so we can't really say. We need some sort of null hypothesis. So in the lecture, I asked you to think about what's our normal null hypothesis for a statistical test. And it is, of course, that there's no relationship. All right, so if our null hypothesis is there's no relationship, what that means in this case when we have two variables is that we only have information about one of those variables, our dependent variable, which in this case is our quiz grade. So if we wanted to guess for all 4 of these students what their quiz grade was, but we only had access to their 4 quiz grades, we would guess that everyone scored the mean. It's a pretty nice, usually in the middle of the distribution, so we want to guess the mean. So if we guess the mean for all 4 people and we plotted that across hours spent watching TV, what we would get is a flat line. So when we're talking about scatter plots and regression, when we are guessing an alternative model, it's going to be a flat line at the mean of y. So for this data, we're guessing that everyone got a score of 5 on the quiz. So when we're going to calculate a mean square regression, that is telling us how well this flat line fits compared to our predicted values. So our mean square regression here's our equation, and it looks a little scary, but hopefully not quite as scary as before our other equations did. What we're going to do is we're going to take our predicted value here, that's our y hat, for each observation and subtract it from the mean of y. Then we're going to square those, sum it all up, and then divide by p minus 1, p being the number of variables. So in this case, if we take person number 1 over here, they got a score of 10 on the quiz. Now, their actual score does not matter at all. What matters is what we predicted for them using our line, which was a 7.5, and what our alternative model is predicting for them. And so our alternative model is predicting a 5 for everyone. So we're going to calculate an error term from the predicted value and the alternative value. So for this person, it's going to be a 2.5. For this person, we're going to predict that they got a 5, and alternative model also predicts that they got a 5. So their error term is 0 here. For this person down here, notice that their actual value is way different from either our predicted and our alternative value. But again, the actual value doesn't matter. What matters is that we predicted a score of 5 for them, and our alternative model also predicts a score of 5 for them. So their error is 0. And then this last person over here, we predicted they would get a 2.5 over here. The alternative model predicts they would get a 5, and so their error is negative 2.5. So, and according to this equation right here, we're going to square each of those. So 2.5 times 2.5, negative 2.5 times negative 2.5, 0 times 0, and 0 times 0. And that will give us a total sum of squared errors of 12.5. Our sum of squared errors is going to be divided by our model degrees of freedom. So the number of variables, 2 minus 1, which is 1. So that's 12.5. So that's how we get our mean square regression. So now we have something to compare 18.75 to. We want to see which one has minimized the error the most, which is a better model. Is it the predicted values, or is it an alternative model? All right, so obviously in this case, our alternative model, just predicting the mean of y for everyone, has minimized the error more than drawing that line between all the data points has. Now that's unusual, but it's actually not all that, it feels unusual, but it's not actually all that uncommon when you have a X variable, that's just not very predictive. It's not very useful. What we see here is that for people who watched a lot of TV, they actually did fine on the quiz. And then we got a person who watched a minimal amount of TV, and they did really terribly on the quiz. And this person who watched no TV, that fits our hypothesis. But these folks over here, they're just not really fitting with our model that TV watching might have a negative effect on your quiz grades. So in this case, in this particular data, just guessing the mean of Y for everyone is a better model than using our hours of TV to try and predict the quiz grades. Another way of saying that is that the inclusion of hours watching TV or X variable does not explain anything more than just having the person's quiz grade on their own. All right, so we can compare the MSR and the MSE to determine how well our line is fitting to the data. What we usually want is for the predicted values, the MSE, to be smaller than the MSR. But as we saw, in this case, our MSR was smaller than our MSE. Another way to think about these two numbers is to create a ratio from them. So if we get the ratio of the MSR to the MSE, that's going to give us an F value. And in this case, a larger F is better. So we're looking for an F value of 1 or above, and that's going to indicate that that MSR is larger than the MSE. So is that there are 3 mean squares. Fortunately, the third mean square is just adding the MSR and the MSE together. So in this case, we're going to add our 12.5 and our 18.75 to get 31.25. There's another way to get the mean square total, and that's by using the actual value minus the mean of Y. So here you can see an example where they're taking the actual values and just taking how far they are from that mean of Y. Once again, you square them, you add them all up, and then you're going to divide by the number of observations minus 1. So in this case, that's going to be 50 divided by 3 is 31.25. And you might also recognize this top number as being the sum of squared errors. All right, so here's a summary of our 3 mean squares and some diagrams about how you get them. The mean square total, like I just mentioned, is going to be the difference between the actual values and the mean of Y. The mean square error is the difference between the actual values and the predicted value from your line. And the mean square regression is going to be the difference between your predicted values and the mean of Y. So now let's get a preview of what your regression output is going to look like. So here's your SPSS regression output. It's going to start with some summary of the overall model, and then you're going to find your mean squares here, and then down here is where you're going to get your the information about the line specifically. So we can find these numbers here. The mean square regression is right here. And you can see in SPSS it's actually labeled mean square regression. Stata is going to label them slightly differently, but don't let that confuse you. So our mean square regression, 12.5 here. There's our sum of squares. We divide by our degrees of freedom, get our mean square regression. We also can see our mean square residual is right here. And here's where you see we are calling it slightly different things. Mean square error, mean square residual, same thing. 18.75, we end up over here. And then our mean square total, you just add 12.5 and 37.5 and you get a 50. We also see our sum of squared errors, which is right there. And then our mean square total is not actually printed there, but you'd be able to calculate it just by dividing it by the degrees of freedom. We also have our F value over here, and it's really nice because it really is just literally that ratio of the mean square regression and the mean square error, 0.667. What we're looking for here is the value to be above 1. So since this is below 1, we can see that adding that X variable does not predict anything more than just having the mean of the cases, the Y variable. We'll talk about how to get a significance test for the F value. But generally, these two will always be in sync together. And then just for fun, to go back to how we drew our line, you're going to see your intercept down here, labeled a constant in SPSS and Stata. And then for each variable, you're going to have a slope. So that is our those are our three mean squares.